Okay. Let's compute its arc length of a curve and reparametrized the curve by arc length parameter. First, let's consider how to compute the arc length of a curve. From the calculus, the one single variable calculus, we know that a plane curve R equals RT may write as XT and YT. T from T naught to, maybe we write as from A to B. From A to B. Then the arc length is integral from A to B, square root x derivative square plus y, the square of y's derivative, and then dt. Or write that is AB, the derivative of RT, the length, the integral of the length of the derivative of RT, or write as from A to B, the speed. That's for the parametrization curve. If the curve is y equals fx, then the length is from A to B square root 1 plus the derivative of f and dx. That's for plane curve. And for space curve, I use the same method to derive the formula of the arc length. So the arc length, that is from A to B, and the length of derivative, the integral of the length of derivative, or write from A to B square root the derivative of x square plus the derivative of y square and the derivative of z square and dt. Use the same method to find the formula. If this is the curve, we divide the curve into small parts. In each part, the arc length delta si equals this line. We use this line. This line is actually is f x y, that is delta x square plus delta y square plus delta z square. Take the square root, and then we divide by delta t square over delta t square plus delta z square over delta t square. And then times delta t. So the arc length. So the arc length is the integral. Well, first is the summation of delta si, then add together, and then take the limit. Let each part let each part to be tends to 0, delta t tends to 0. We got this formula. That's the arc length for space curve. Now we look for an example. Find the arc length of RT equals cosine t I plus sine t j plus t k from t equals 0 to t equals 2 pi. Use this formula. The s is from 0 to 2 pi. R prime t, the length of R prime t and dt. The derivative of RT is negative sine t, cosine t, and 1. So the length of the derivative, that is square root sine t square plus cosine t square plus 1. So that is, the result is square root 2. The arc length, so the arc length is from 0 to 2 pi, and integrate square root 2 dt. So that is 2 square root 2 pi. As the arc length. The second is the arc length parameter. If for any t, if t is a variable, for any t from t to t0, find the length from t0 to t, and the length from any t. Here is t0. The length is actually the integral from t0 to t. The length of the derivative of RT dt, because t is changing from time to time. Maybe we use another variable here. Maybe use tau, d tau. Then s is a function of t, because t is changing from time to time. So actually s is a function of t, and the length, the arc length, is increasing by t. So there's a inverse function of t, is t. We can view t as a function of s, and we call that s t is arc length parameter. And the ds dt actually is the derivative of RT, the length of the derivative. Because s is increased function for t, and hence there's inverse function that t there's inverse function, so t can be can be regarded as a function of s. So for any t, we can write Rt as Rs. That is reparametrized the curve by arc length. Because the S is increasing, it's monotone. And how to reparametrize the curve by arc length? First, we evaluate this integral and then write t as a function of s and insert to the equation of Rt. Let's use example. Reparametrize Rt equals cosine t, sine t, and t by arc length. First, we find the representation of S in terms of t. As r tau, length of r, derivative of r tau, t tau. That's t naught to t, square root 2 d tau. So that is square root 2 t minus t naught. The t naught is constant, and hence by arc length may be curve by arc length. And from t not equal 0, maybe this is easier. So here the t naught is 0. Maybe it's easier. So that's square root 2 t, and hence t equals s over square root 2. So the Rs, we replace t by s over square root 2. So the Rs is cosine s over square root 2, and sine s over square root 2, and s over square root 2. That's representation by arc length. Why we use the arc length as a parameter for a curve? Because there's some advantage. If r equals rs, that is representation or parametrization by arc length. If the curve is parametrization by arc length, then the length of the derivative is a unit vector. Is a unit vector. We call this as T. We use the dot over the arrow. It means that is the derivative of arc length. It's called unit tangent. If the curve is parametrization by arc length, parametrized by arc length, then its tangent vector is a unit vector. And in general parametrization, the T is the derivative of RT over the length of the derivative. And why this is true? Why this is true? Because Rs equals the unit tangent vector. Since dr, we use the chain rule to derive this formula. Dr ds, that's dr dt times dt ds, that is rt, the derivative of rt or r prime, rt prime, times ds dt, that is 1 over dt ds, that is 1 over ds dt, because ds dt is the length of the derivative. So the dr ds is actually a unit vector. That's why we use the arc length parameter. Okay, let's take the third example. Third example. If RT is 12 sin t, I plus 12 cosine t, j plus 5t k. Find the unit tangent vector. At t, the unit tangent vector at and t just equal, just t equals 2 pi. The solution is we can use both formula to find the unit tangent vector. For in general we use r prime t. R prime t is 12 cosine t, 12 sine t, negative 12 sine t, and 5. So the length of RT, R prime t, that is square root 144 plus 25. That is 13. So the unit tangent vector when t equals when t equals 2 pi, that is R prime t 2 pi, that is 12, 0, 5. So the tangent t, the unit tangent at 2 pi, that is 12 over, we can write as R prime t at 2 pi over R prime t at 2 pi, the length, that is 12 over 13 and 0, 5 over 13. That's the unit vector at 2 pi. This is the first way. The second way, we first represent the curve by arc length. So the arc length is from 0 to 2 pi. We can start from 0. That is square root. The formula is R prime t, the length dt. No, that's from 0 to t. So the arc length from 0 to t, square root, that is 13, not square root, that's 13 dt, so equals 13t. So et equals s over 13. So the r can be written as rs, that is 12 sine s over sine s over 13, and 12 cosine s over 13, and then 5s over 13. And when t equals 2 pi, s equals 26 pi. So the derivative of rs, that is 12 over 13 cosine s over 13, negative 12 over 13 sine s over 13, and 5 over 13. When s equals 26 pi, here is 12 over 13, 0, and 5 over 13. that is the tangent vector, unit tangent vector. That's why we use the arc length parameter. In the theorem, in the curve theorem, the arc length is much easier to use to compute some geometry quantity, some geometric quantities. That's why we use the arc length. In the next video, we start the finite frame. Then we use the arc length first, and then change to the general parameters.